Hello. Okay, in this video we're going to have a look at using the multi-sim simulator to analyze the performance of our bipolar amplifier, our common emitter amplifier. So we've seen in the class lectures and also in the tutorial example, we've effectively designed an amplifier around using this particular transistor, the 2N2222A. This was the transistor that I used in the other video to generate where I generated the transistor curves for just the transistor itself. In this video we're going to look at that incorporated into the common emitter amplifier. So if you look on the screen, this has all the components that we've discussed in the other parts of this course. So at the center of it obviously is the transistor, and here is the collector resistor. These are the emitter resistors at the bottom here. These two resistors here are the biasing network, and then obviously we've got a signal coming in, a very small AC wave. We've got our filter, our capacitors, our capacitors here at the input and at the output, and this is the so-called bypass capacitor. The other thing I've added here is a load resistor. So this resistor is like, it represents the load that the amplifier is transferring the signal into. So that could be a pair of headphones or another amplifier or something like that, or a computer system of some kind. And then I'm going to use the oscilloscope to monitor the voltage at the output point here and also at the input over here. So this is my circuit, and the values that I've put into for these particular components are the ones from the tutorial example that goes through the design of the common emitter amplifier for this particular transistor. When I run the simulation, the oscilloscope will record the voltage values, and this is what I would get here. I can stop it because it's already recorded quite a few cycles of the amplification. And now what I've actually got here is two curves. Channel A is the actual output. If I just shrink, sorry, that's the wrong way. If I increase the scale of that to 5 volts, you can see that the output, which is actually, if you watch the screen, you can see that it's the first curve here. That's it there. That's got a peak-to-peak value of about 8 volts from that top peak there down to there. And the input is on a much smaller scale, 50 millivolts. That's got about an input of 100 millivolts. Peak to peak, and that's actually what I specified over here on this voltage supply here. So my amplification is just the values of these voltages divided by another, 8 divided by 100 millivolts. So that gives me a amplification factor that I need. I think it's actually a little bit less than 8. It's probably more like 7 between the top of there, but I can measure that if I want to. And if I want to measure that, what I would do, for example, a very easy way to do that is to use one of these probe devices here. So these are various types of probes, and if I take a voltage probe, for example, and I put it there on the screen, now I run it again, it will then give me the values. And in fact it says the voltage peak to peak is 6.73. So my amplification is going to be 6.73 divided by 0.1, and that will give me an amplification of about 67, which is very close to the value that we calculated in the tutorial sheet. So my circuit actually is behaving exactly as I want to do. I can explore the effects of other things as well, for example. So we talked in the class notes and in the tutorial about the importance of the bypass capacitor down here, for example. If I change the value of that bypass capacitor now from 33, and maybe I'll put it down to 1 microfarad, if I now rerun the simulation, you'll see now that the output peak goes down a great deal. And that's because the capacitor is no longer acting effectively as a bypass, and then the effect of this high value resistor here, the 240 ohms resistor, is bringing down the gain. So it shows you can experiment with these circuit values in real time to check that your understanding is correct. So I put it back now to the 33 that we calculated and immediately you can see this peak comes back up here, and I see here that my peak is back up to 6.73. So my gain is now back up to the values that I was expecting. I can also play around with changing these, for example the biasing here, and then I'll see the gain change and so on, and so with all of the other components. So once I've got this circuit drawn, which takes a few minutes really with the multisim, then I can very easily experiment a little bit with the values to check that my understanding that I've got, my theoretical understanding, is correct. But as you see, with these values that we calculated in the tutorial, we get very similar results with the simulator to our theoretical calculation, which is very reassuring, and it tells you that our analysis was correct. So I hope you found that useful. I'm going to encourage you in some of the other tutorials to take this circuit and experiment with it a bit more and see if you can understand the effects of things like changing the value here of this gain of this load resistor, for example, and changing the values of the other components as well.